All right, ladies and gentlemen, hello and welcome back once again to the longest running show in the world about data. It's called DMRadio. Yours truly, Eric Kavanagh, here in year 18 of the show. Yes, we were founded in February of 2008. It's a long time ago. The more things change, the more they stay the same. And I'm so excited, folks, to have one of my best pals in the business on the call today. A guy who knows more about quantum than any person I've met and has amazing ways of describing things and explaining things in human readable language, which is some good stuff. And that is Sean Michael Brehm. He's now the chairman of Spectral Capital. You may recall him from CrowdPoint Technologies, the Node Nexus Network. He's got a number of companies that he's baked in here, and there's some really cool plasmid technology, some new chip design components that he's been talking about lately. Long story short, we're going to talk about quantum and what quantum really means for quantum computing. There's been some cool stories in the media lately. There was a story about some problem that would have taken traditional server architectures years to solve, and quantum did it in like an hour or 2 hours or something like that. And it is because of a whole variety of factors. But let me go ahead and bring in Sean Michael Brehm. Tell us, first of all, how are things going at Spectral? And let's get into the reality of quantum, what it's going to take for this to revolutionize how we process data. Because everyone's excited about large language models. We did a show yesterday and we explained, guys, if they're 80% accurate, what part of your business could be wrong 20% of the time? Not much. So there are
Yeah.
real warts on these things, and they are frankly borderline catastrophic depending upon how much you invest in them. But let's talk about quantum, Sean, because that is one of your areas of expertise. What's happening in quantum? Where is it going?
Yeah. I think what's happening in quantum right now is it's perfect. I think it's apropos that, DM radio, all about data, is talking about this, is quantum computing is really going to redefine the love affair that we've all had with our data. And you and I have talked about this many, many times, that for those who haven't, I've been a firm believer, and you have, along with many of your peers, that data, is the new oil, right? And this kind of oil has multiple properties. It's got variability in the data. It's got veracity in the data, and it's got velocity in the data. But the most important thing about data is the value that it has.
Mm-hmm.
And data with value is information. So if you think of data as the new oil, information is really kind of the fuel that powers the global economy. And the way the average person, because this show is all about data, we're going to make it tangible for quantum. The way you as a listener or viewer of this video has to think of data is data has to kind of navigate away from all those 6 variabilities that are in there. And it has to get to the most important component, which is value. And value is really defined in 4 simple components. Think of data as, think of oil with petroleum engineers. I think we've used this analogy in the past. You get these petroleum engineers and they know exactly how to refine the oil for the fuel that's going to power your car, or the fuel that's going to power a rocket ship, or maybe an airplane, or maybe a diesel generator. So they know how to refine it for the outcome. Well, quantum computing is just that capability. It's going to have the ability to refine it at scale such that it will be able to provide spatial context. In other words, where's this at? Where's it being taken place? It's going to have temporal. When did this happen? Is it happening now? Will it happen in the future? And then it'll be able to derive the overall theme from the data, so then it can be explained in a way that is semantically aligned to your understanding. Because the way you might describe it to a physicist or a mathematician or an 18-year-old is different. And quantum computing literally gives us the ability to achieve just that. Take that raw data, refine it at scale, so that it can then be given those 4 attributes of here's where it's at, here's when it's time relevant, here's the theme of it in a way you can understand. And I'm going to describe it to you semantically so you can find the value of this data, which is now information. So when you think about data and its relationship to classical computers today, you have to, and versus quantum, you have to kind of look at classical systems are essentially like what you have right now on your phone or your laptop. It's just a really fast light switch, right? And each switch is either on or off, and there's nothing in between. That's the state of computing today. And the idea is
binary, right?
It's binary. And the way that happens is through semiconductors. Now, semiconductors are not a bunch of switches, right? It's just really about facilitating the switches. And essentially, if you think about it, a semiconductor, it's like, I don't know, imagine Venice. If you're looking at Venice from top down, there's a series of canals. Some canals are really wide and some canals are really small. And then they move little gondolas or boats or taxis, if you've ever been there. But think of instead of that being water, you put in things like gold and metal. And then what happens is you stack about 8,000 Venices on top of each other, and the ones and zeros move through electrons. And so those electrons are moving through this metal to basically hold a bit or a byte, on or off. That's what it is. Nothing in between. It's really simple process. It's been semiconductor manufacturing 40 years, going back to the heady days of Moore's law and guys like Bob Noyce and Andy Grove at Intel, who are just like giants, it's in the world. That industry is supposedly today at its limit, because now everybody's saying, well, quantum's going to flip the game because we're going to go to a quantum bit. So that's what we call a qubit. And it's not just on or off. It can be both at the exact same time. So it's like spinning a coin. And that's spinning a coin. That's when you hear people say superpositioning. That's what they mean.
Well, and so think about what this means. Now, you're going to have with these new chips, they're going to need new boards, they're going to need new software, they're going to need, to your point the other day, a new operating system. I mean, how much of this stuff has been built? And that's a long arc. I mean, you just talk about building a new database. One of my best friends knows databases like the back of his hand. He says it'll take you 10 years of a database in production to find the edge cases that'll crash it, right? So you think an operating system, I mean, Linux is the de facto standard now. I know one of the guys who is the maintainer for the Linux kernel. That's a pretty important job, right? So you're managing the kernel. They're doing very, very cool stuff with being able to move massive amounts of data around because they've decoupled the metadata file management. It's basically a parallel file system. So they're doing really, really cool stuff there. But are we like, who is building the OS for quantum? Is that something that IBM is building? Where's this stuff going?
It's a great question. And I've got kind of, as usual, right? I've got this obtuse view on that, because the current groupthink on quantum computing, I think, and I said this, recently on Fox News, we have a lot of scientists, amazing scientists. You've had Dr. Wolf Kahn, with me, a great scientist, preeminent scientist, MIT, University of Washington, built the AI labs at, many major institutions. So like he's a bona fide genius, but even he will admit to you that the current approach in quantum computing has been largely led by scientists. And what we've been doing, with the team and the ecosystem around us, is working with engineers. And so when you think about quantum, there's emerging camps that are coming out right now. Most of the camps are, hey, we're going to manufacture these qubits. These qubits have really weak signals. So because they're so weak in signals, we got to make sure they're protected. So what we're going to do is we're just going to change the entire environment for this weak signals, and we're going to freeze it to absolute zero, something called Kelvin. And we're going to make it so cold that it kind of slows down everything, so that as you move these qubits, which are really weak signals, they'll move through time and space in an environment where they won't bump into something that will damage them. And that's certainly the current best in class thinking. And then when you have that best in class thinking, rightfully so, guys like Jensen Huang come out and go, look, real application of quantum computing is 10 to 15 years out. And he is absolutely right if you follow the current process.
Mm-hmm.
He's absolutely right. But there's a few of us going, why will we throw the baby out with the bathwater? Like, we've got 40 years of semiconductor experience. Why don't we leverage 40 years of semiconductors, and let's leverage that knowledge and slightly modify them to basically move qubits? And that's really interesting, because now all of a sudden is you can start going back to that data thing. You can start going back to, here's the deal, because you have to stay focused on why you want computing. And it's all about the data. And as we just said, regular data is about bits, ones and zeros, and quantum data lives in states. They're really complex. They're probabilistic. They have all these weird combinations. And so that means that quantum systems will be able to crunch massive amounts of data into information simultaneously. And so you want to look at, can we do this kind of in the way we've done semiconductors in the past? And that's really where we're at right now. There's two camps emerging. The engineers saying, why don't we take a look at semiconductors and see how we can reuse the majority of that? And the other guys who are scientists going, well, why don't we just go ahead and spend a ton of money on theory, and who cares? It's a race to the end. And whoever wins, wins. So, and then there's some implications of that. The implications are even bigger to the American people, to the world.
Yeah.
Well, if you're going to build these big, heavy systems that are essentially controlled by a few people, right?
Right.
Don't know if I like it.
Well, so I mean, you bring up a whole bunch of good points here, and let's talk about from a data management perspective. Well, data management is just prep. You're just preparing to be able to do something later, like analysis or transactions or whatever. Data management is prep work. It's like the sous chef, right? It's not the chef. The chef is the person who is leveraging the data management that allowed them to ask questions, do queries. And you think about, how much things have changed. I just explain all the time. Just yesterday, we talked about data warehousing. 30 years ago, you had expensive storage, thin pipes, slow processors, but still a need for data. You couldn't query the operational system, so we came up with data warehousing, right? Okay, fine. And as an
ETL.
industry evolved, and all this ETL is just out the freaking window, ETL, batch windows, just total nightmare. Well, I mean, these new foundation models kind of throw all that cattywampus, and they are probabilistic. This is a problem because I was joking that, and let's see what you think about this. Over the past 50 years, all of the innovation around information systems has focused on making databases faster, more performant, more reliable, have more concurrent users, but accuracy was never in question. It was table stakes. You would always get out of it what you put into it. Hands down, no
100%.
one would even question that. And
100%.
now with Gen AI, we're putting a noise filter at the end of that long process, throwing the baby out with the bathwater, right? And I'm thinking to myself, that's crazy. And so now there are all these RAG models, and graph RAG looks very, very promising. But all that stuff kind of goes out the window in a quantum world, because in
100%.
quantum, you can do all these analyses like on a moment's notice. I don't have to worry so much about all this data warehousing and all this crap.
Nope.
And that's what I think is so fascinating. And maybe let's run with that analogy for a minute here, because all of a sudden you realize, well, wait a minute, I don't have to do all that other stuff, because I can just ask a natural language question to get the answer I wanted. Are you serious? Like this is possible? And the answer is yes, right? In the right context. But, again, until we're there, until the systems are deployed, you can't use the system that isn't deployed. So we're not there yet. But this is what I'm saying. Like that is how disruptive the process is. And it's like, well, what does that mean? Do we let go of this whole old environment that we have? Like how is that going to change? If you're a net new company, that's one thing. If you're a legacy company, you have all these systems in place. That's a very difficult nut to crack. But what do you think?
No, first of all, wow. I mean, ladies and gentlemen, this is why it runs DMRadio, because he's lived through this data process. Let me kind of summarize it, because what you said, anybody that's been in data is like, okay, this guy really understands data. When you go back to the days of data management and data warehousing, extracting data, transforming it, and
Right.
loading it to a system became a really big need. And then once you got it loaded into some kind of data lake, then you had to start figuring out to do sense making, right?
Mm-hmm.
I had to do sense making about this because I've got all this disparate stuff. And so then we got into machine learning. Remember that ML
Mm-hmm.
back in 2013 and 14 was like the thing,
Right.
right? We're just going to do machine learning, and we're going to run across all this data, and we're going to do distributions and frequencies and co-occurrence and k-means. And we're just really going to essentially sort things in more buckets.
Right.
And at that point in time, I think is where the current AI guys went this direction, and some of us went the other direction.
Hmm.
And those of us that went the other direction started looking at this and said, this doesn't make sense. This doesn't make sense because there's no one's really defining the entropy in this data.
Hmm.
And we're not really establishing a way to treat this data as some kind of sensor. Because really, when you think about data in a data system, we ran machine learning on it, but we first should have treated it as just sensor data. And we should have figured out, okay, as we go through this data using some kind of entropic approach, what are we learning from this? Non-regressively. In other words, let's not look backwards. Let's look at real time, not only what's currently in the data lake, but what's coming in it. And let's figure out, are there any rules that are kind of emerging? Are there some soft rules that we're seeing coming out of this? Are there some hard rules or some absolute rules? Because then once you start getting some rules, that kind of gives us the real foundation for a more authentic version of intelligence. While the rest of the world was just smash it all together and just turn a large language model, right? And
Mm-hmm.
that's where we're at today. And what I thought you said was so insightful a second ago, which is when you look at where quantum computing's going, and I've seen it in the lab, you're talking about the ability to take a terabyte of data and run it at once. Now, you're probably going to agree with me, and you probably add some color to it. Your average size of a large language model is anywhere between 500 gigabytes to about a terabyte. And with quantum computing, that's all persisted in compute in real time.
That's
So then,
crazy. Hold on. Let's put a thumbtack in that. We got a commercial break coming up here. We're talking to Sean Michael Brehm from Spectral Capital, talking all about quantum and how it's going to affect the data world and when that's going to happen and what you can do about it. We'll be right back. You're listening to DM Radio. All right, folks, back here on DM Radio, talking to Sean Michael Brehm of Spectral Capital. We're talking about quantum, how quantum is changing everything, or will change everything, I suppose. And we were talking about data management and all these practices, these legacy practices of loading data warehouses and having some latency to that. And then we just decided to make the same mistake again, not really a mistake, but with data lakes. Okay, let's get all the data lake in one place. And the guys that I talked to yesterday from Data Squared are pretty clever. They're like, no. We're just going to ping all these systems as we need to, and we're not going to just physically try to consolidate all your data. It's another way to do it. But the point is that quantum can really change all that. And we're going to have to figure out how that changes workflows and business processes and how you do things and what the cost is and all this stuff. And I was just talking to a guy, Stephen Klein, earlier today, who is really throwing shade at these large language models and the OpenAI business model. And of course, Sean knows a couple things about those guys too, and how these guys are losing $1 billion a month, they think. And what are they really doing out here? It's the freemium model, get you addicted, pull the string on it, and it's still only 80% accurate. Well, again, even if it's 90% accurate, what part of your business can be wrong 10% of the time? The answer is not much, right? Like basically nothing in your business can be wrong 10% of the time. Accounting, operations, fulfillment, no. Your reporting, none of that stuff can be wrong 10% of the time. That's crazy. What was someone telling me? Like 3% is like, all right, well, hold on. We're not at 97%. But quantum, again, because you can have this superpositioning, because you can process so much data so quickly with all these different rules, it's just a complete total game changer. So just jump back into where you were a minute ago. You're talking about how quantum can just soak up massive amounts of data, but does it have to be turned into qubits? I mean, like, how do we actually get there where our data can be ingested by a quantum chip?
yeah, great question. So when you look, there are ways to transform data in a massive data lake if you build pointers in a classical system that tells the interface. First of all, you're going to need a quantum virtual machine, right? You don't hear that conversation very often.
Right.
And that quantum virtual machine has to kind of be a polyglot, right? I mean, it's got to speak everything from curl to Spark and Kafka. It's got to speak all the languages so it can literally become a microservice. It says, hey, I kind of understand this legacy stuff. And then it's got to be able to take some kind of schema that you're pulling in that has to be completely amorphous. So it can just, you don't care about, it just needs to be, you know, you just want to be able to pull data in the form of epochs pretty quickly. And then you want to be able to say, okay, quantum system, I've gone ahead and I've run these series of algorithms on it that now make it in a format that you can process.
Mm-hmm.
And so you're not talking about ETL anymore, right?
Wow.
What you're talking about being able to doing is leveraging massive amounts of data sets as nothing more than sensor data. Think about that. You're now, so you, as long as you can put this data in a format that is consumable, right, and is repeatable, and you can define some kind of coalitions within the data as far as user management and rights management, and you can, oh, by the way, make sure it's quantum, post-quantum secure, you know, danger Will Robinson, right? It's got to be secure, right? Well, once you do that, now all of a sudden you have the ability to essentially not even care about large language models anymore. Because I can take a, let's give a simple example. I can take a large corpora of your automobile, whatever your car is, and I can take that and turn it into, let's say, a Toyota coalition, Toyota, whatever model car you Toyota. And you can literally now have a conversation with your car. But it will only, and I've showed you this working, right? Do you remember when I showed you that? I don't know, right?
Yeah, right.
So the problem you get then is certainly it will be able to talk to you about the car, but if you begin to entertain logic associated with that is extra or outside of what the manual says, it won't be able to do any kind of inductive thinking or deductive thinking. It's merely just going to give you a conversation around the vehicle and only the vehicle. And I think I demonstrated you something like that where it asked a question, said, I don't know. So now what you start getting into is some really fascinating concepts, which is now you can start taking, well, why don't I create a collective intelligence where I can take the best inductive and deductive thinking and methodologies and then make it a joint coalition with your car manual. And now all of a sudden that becomes the corpora or body of your sensor data, and that sensor data can be decentralized around the world, and you've got this kind of quantum virtual machine that can define the parameters, figure out what application language that is running, or application agnostic, and then merely position it to persist into qubits, and then superposition it so that you can ask it a million questions in real time. And then when you're done, dump it. I mean, that's where we're going.
That's crazy.
And the question you have to ask yourself is, do you want to take the current stewards of the internet who've done so well with it and say, you know what, we're going to go with a centralized model and we'll bring us data and we'll 100% believe that whatever results you get back about, I don't know, drug discovery or maybe cure for cancer, and you'll promise you'll share it all with us.
Yeah.
Right.
And
no transparency. So I think the most important thing that has to happen as we get into the quantum era is these corpora of data sets that we're talking about have to be resilient. They have to be decentralized. They have to be able to speak both quantum and classical compute systems. That means they have to speak many different software languages, and they have to be under the control of the owners with the ability for sharing it with other corpora.
Right.
And that's really kind of our view on how data needs to look in the quantum era.
Well, and you've built out, I think you call it Quantomo. Is that right?
Yeah. So we built a couple things. So many moons ago in an organization, so they're going unnamed, we solved a problem in a very sensitive part of government where when you look at threat to the United States, there's so much data out there. We don't know what we don't know.
Right.
And we don't know what questions to ask. Right. And I would, if you disagree with that in today's current data systems, I'd love to, I think we're still in that state, right?
Yeah, right.
And that was the problem. So how do we get to something a priori that says, hey, spatially, this is the problem that's happening. It looks like it's happened already, or we think it will happen. And here's the kind of theme within political, military, economic, social, information, and infrastructure. And here's what it means to you, certain organization within a certain country or region. a priori, which means, hey, heads up.
Right.
So we started building in 2016 quantum algorithms when nobody was using the word quantum, right?
Hmm.
And as we started building those quantum algorithms, about 3 years into the program, it had been about 2000, about almost 4 years in the program, we saw that we were hitting a roadblock on how to literally create a data system. So then we started building a distributed quantum ledger database. Now, you and I had conversations with that 4 years ago, 3 years ago, but we didn't really tell anybody what we were doing then.
Right.
Right. At the same time, we were building a quantum chip that we never told anybody. Because can you imagine when you and I were talking on DM radio 3.5 years ago? That I
Right.
said, hey, you know what? We're building a quantum chip, right?
Right. Right.
What?
You're right. Right.
Yeah. Yeah. So we've kind of been in this for the long haul. And so what we've done is we said, well, gosh, we learned a lot of really cool lessons, with some taxpayer help. And it's really helped a lot of people. And we were able to wrestle that technology back. And it's essentially a quantum algorithm that uses analytic tomography. And what tomography says is there's a bunch of sensor data out there. We're going to create this ability to look across this massive sensor data. And we're going to basically run mean field Hamiltonians on it using a cooperative and distributed inferencing approach that allows us to begin surfacing non-regressive. And instead of looking at the past, we're able to start looking at what's happening in real time and forecast the future. And then based on our forecast, determine whether the rules that are coming out of this data are absolute, like, yep, they're going to happen. They're hard, pretty much going to happen, or soft, like, kind of, right? And now we're at a point where when you couple that lesson we learned with a massive distributed quantum ledger, like a blockchain, but that's also a database. So now you have immutability, custodianship, and transparency at the same time. And you're able to create these epochs of data that have a unified model for defining, in a header, the coalition it belongs to, the spatial, thematic, temporal concepts very quickly with addressing mechanism to its related previous, data sets, and then an epoch content where it's literally presenting you the data, and then a footer that can kind of explain to the quantum system how to process it, as well as links to associated data. And you can do this both in a classical system. Works directly with, it has interfaces into things like Cassandra or Snowflake or Elasticsearch, and it can work with quantum chips. Now you're kind of in a really interesting space. And that's really, we were blessed enough to solve big data problems at both the governmental and business levels, that we think we're in a really unique position now, both as CrowdPoint and as Spectral, because Spectral purchased one of the first quantum algorithms to facilitate that mean Hamiltonian.
Yeah. No, this is very interesting stuff. And I think that, we've talked about this before. I love this concept of a quantum bridge, because basically, and you think, so what are companies doing now to be able to leverage large language models? They're using RAG models, retrieval augmented generation. I mentioned graph RAG. It's almost like, I think about like what is it in your car? The flywheel in your car, right? It's basically allowing you to manage the imbalance of forces on either side in this middle piece, basically. And that's kind of, I think, what your quantum bridge idea is all about, because you're also leveraging this quantum ledger database. For some reason, iceberg tables come into my head as another example of how to connect worlds, right? Because that's what you're doing. You're like, I've got this super processing power over here, but all these legacy systems over here. How do I harness this and feed the important things into this environment? And there are all kind of ways you can do that. Obviously, there's 1,000 different ways you can do that. But what do you think about that analogy, and how does it apply to what you're building?
No, I think it's a perfect analogy. Like you've been lucky enough, I think, one of the few people on the planet that I've allowed to come in the back end and look what it looks like. And it's a perfect analogy. And that is because now all of a sudden, as I said before, you are the progenitor. I've been saying this since you met me, which is the human identity is that is the progenitor of commercial and capital markets. So when you think of traditional databases within companies, 99% of them have this information about you.
Right.
They want to sell you stuff.
Right. Wow.
So when you think about why there's $11 trillion in cybercrime, because everybody just wants to get stuff about you to sell you more stuff.
Right.
And so when you start building systems that are human-centric from day one, and you're able to tie commercial activity back to, or back up into capital activity, you now have and you're able to abstract the human identity and use things like post quantum security. Now all of a sudden, you're redefining machine learning. And our current
Mm,
approach is redefining, because now all of a sudden everybody's medical records are out in the open, but I don't know who I'm talking about.
right.
Right? It's impossible to see who this person is. We used a quantum encryption method that is post quantum secure, and you're the only person that knows it, or your
Hmm.
doctor, and that's for
Wow.
limited. So it's we're still at the. This is so transformational. I got to be honest with you. There's times that we're learning, you
Right.
know, on a daily
Sure.
basis.
Sure. Well, so I'm trying to think what are some practical applications as this stuff comes online, right? You think about with the LLMs. Right now,
Yeah,
we're kind of doing time sharing, right? And as we talked about earlier today, I mentioned this guy's like, dude, they're losing money on every single transaction they make. Is OpenAI is they're like $40 billion. They just got in terms of financing. That'll last them about almost 2 years at the
yep,
current burn rate, which is insane. Like it makes no
yep.
sense. Then you get DeepSeek out there distilling their models, offering a 98% discount on what they're doing for more or less the same kind of
Still
results.
regressive.
And like to your point, that's interesting. So it's still regressive. And what you're doing is using these other algorithmic approaches to be forward looking based upon which is predictive analytics, but it's
Yeah,
much richer, more accurate predictive analytics that's based upon the activity right now. And I love this point you're making about sensor data. View everything as sensor data and just ingest all of that and like look and see what's going on. I think there's an interesting analogy too to how the LLMs give you the output, right? We talked about this on various shows. It's a lossy process because you're
yep,
converting text or images into vectors because you can't crunch letters and you can't crunch images, but you can
yep,
crunch data. You can't crunch numbers is the
yep,
key. So, but it's a lossy process, right?
100%.
But
And it's still regressive.
and it's still regressive. That's right. It's still looking backwards, basically.
Yeah,
So
yeah,
what you're doing is, and there I'm a big fan of what I call natural law, right? I'm sure you've studied this, right?
100%.
Natural law says, look, the world works a certain way. Figure that out and don't try to push it too far. And our break is coming up here in just a second. We'll pick this up after the break. But natural law says, look, the world works a certain way, and you're not going to change the way the world works. So you should harness what's out there instead of trying to change. In English, we say go with the flow. In Chinese, they say don't push the river. It's the same thing. It's just a different perspective. So don't push the river. Now you can build a dam, and then you're harnessing the energy of natural law, but you're being cognizant of what is actually happening. And I think, to your point, a lot of analytics is regression oriented, which is looking backwards. Well, guess what? Things change. I mean, things change in markets, things change in technology. So, in that sense, the sort of laws still apply, but it's a much different world, and you have to be careful about trying to retrofit whatever you have into the past and think that's going to work in the future. But we'll be right back. You're listening to DM Radio. All right, folks, back here on DM Radio talking to Sean Michael Brehm of Spectral Capital, all about quantum, how much it's going to change things. I think what you're going to get is you're going to get some, obviously, it's in life sciences now where there's a real need for it, right? Life sciences, you have really hard problems with incredibly dimensional data structures that are big, huge. My friends at Hammerspace do a lot of work in this space with their parallel file systems. But that's certainly a use case for for and also security obviously because like one of the best presentations I ever heard was an Indian gentleman in Malaysia, and he was talking about security, and he said so basically what I'm trying to say is that lunch is not a food. And I laughed because his point was lunch is an event at which you eat any kind of food, right? But lunch itself is not a food. So security is not a thing. It is a practice. It's a discipline. You have many different technologies that go into it. It's all sorts of layers and everything that you can have. Alerts is usually what it boils down to, and trying to understand what that thing was. Well, quantum can do that just 24/7 all day, analyzing incredibly I mean, you think about a company like Splunk and what they do with tracers and logs and metrics and like coming up with all these views, and these people sit there all day in front of these screens, and like I'm like, how do you do that all day? It's just crazy. And you don't even know if you're on the right track. Maybe it's just a fluke. Maybe it's something else. Who knows what this thing is? My point is that quantum deployed appropriately could just obviate the need for Splunk theoretically. What do you think?
100%. I mean, you remember when we were growing up, all of us, well, if you made a point to someone, they're like, well, what does that have to do with the price of tea in China?
Yeah, right. Right.
With quantum,
Yeah, right.
like, because you can find non-obvious discoveries. So let's take your cyber example. So right now, if you look at cybersecurity, it's performing so well. We're now up to $11 trillion in cybercrime.
Right.
Cybercrime costs aren't going down. They're only going up. I mean, it's the most incredible indictment on an industry when you think about it,
Wow.
right? Still going up, right? And so the answer of the cyber industry is, oh, let's just blame the user, which is
Right.
a horrible thing. But let's take that. So let's take a look at kind of deconstruct what this does in cyber, what it will do in cyber. Right now, you've got all these attackers that are somewhere out in the ecosystem, and they're setting up servers to basically come in and get to your perimeter. That's usually run by a firewall. And then if they get through the firewall, they're going to navigate what we call east, west, and north, south within your network segments.
Right.
And the goal is to eventually get down to your endpoint, right? To that server, to that laptop, right? So those 4 layers literally have lots of stuff to go in it. And so that means that companies like Splunk are running analysis on potential threats, but really, they're really not. I mean, it's really a signal to noise problem, right? And so the problem is there's so much noise that it's really hard to isolate the signal. So again, they're aggressive. Well, these customers were hacked using this and this and this. And therefore, I'm going to apply a probability weight on it that when we see this moving east-west, it's going to definitely be a threat, right? But the analysts are still getting like good idea fairies going bing, bing, bing. I have an idea. I have a good idea fairy. This might be a threat all day long. To your point, how do you handle that?
Idea fairy.
Yeah. So let's think about what happens with quantum. Well, quantum sits there and says, I'm going to run an analysis on your entire network. I'm going to take a look at every single software you have on there, ranging from mobile phones to endpoints to even old SCADA systems. And I'm going to go back and look at all the NIST data and find immediately what the past exploits have been and give you an automatic. I'm going to immediately run, basically just like you would probability of death. I'm going to basically run a probability of breach model. And then after I run that probability of breach model, I'm going to run analytics and I'm going to say, okay, what are the ports necessary within each network segment based on the software we have? So I've scored the risk, and now I'm going to look at all the necessary ports at each network segment. And then I'm going to find out which ports aren't necessary with that segment. I'm going to tell you exactly which ports to lock at each network segment. And then I'm going to look at the firewall and say, all the network segments that have ports that are unnecessary, I want you to tell the firewall to block it. I've just gotten rid of the huge network signal to noise ratio because I shouldn't have anything moving north, south, or east, west outside these required ports. And it's going to do that in a millisecond.
Wow. Right.
Okay. So cyber guys out there, you're out of a job.
Wow.
Right?
That's
because
crazy.
you're going to have battles. What's going to happen in the future of quantum computing, you're going to have battles in the ecosystem long before they get to your firewall.
Wow. That's crazy.
Yeah. Yeah. It's a
Well,
deep
listen, let's talk about this quantum chip that you've been working on too. I don't know how much you can reveal in a public forum here.
Yeah, very
but
little.
yeah, okay. So, but the point is, like, there's all this effort being put into chips, and you've come up with some pretty creative ways
Yeah.
to get around that. And this is what I love. Like, one of my friends, he's a developer. He's got this great line, this great mantra he lives by, which I'm sure you're going to love. He said, "Busy is the enemy of creative." Because if you're busy all the time, you're behind the 8 ball, right? If you're creative, that's when you're sitting at that's the inference layers, right? I mean, that's what an
Yeah.
inference layer is. It's like, what should I
Yeah.
make of all this? And then
Yeah.
what should I do next, right? And then
Yeah.
like with AI agents, beliefs, desires, and intentions. Have you seen all this? Like BDI, I call it the BDI index. It comes
Yep.
from psychology, but they're applying it to, and it kind of makes sense now. I'm like, all right, I can kind of see. So the agents, they have X number of beliefs. They have desires, which is stuff that's supposed to be working on. Intentions is my plan for how I'm going to do it, right? You get log files, tell them what they're doing. You have to orchestrate all these things. It's going to be really, 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 really interesting on the agentic AI state. And then to your point, like once quantum is material, once it's in production, I mean, that's just a whole new way of solving all these old problems just in real time. Solve all those
Yeah.
problems, solve all these problems, like just all day long. So
Yeah.
what can you tell us about your quantum chip or Spectral or where you're going?
Yeah, yeah. So Spectral is in the business of building micro data centers today, and they're doing it leveraging technologies like the quantum analytic tomography component built directly into classical systems, and it is building these micro data centers powered by wind and solar and hydrogen extraction, so that we can literally start powering AI by returning power to the grid. We can actually produce about, you know, 5 to 8 megawatts a day. So that's about 3 gigawatts a year. And we're only using about 2.5 megawatts to run a micro data center. And we're actually able to give energy back to the grid. So our short-term strategy is build these micro data centers in a way that we can begin to start decentralizing for the quantum era. Because here's the truth of the matter. When these quantum chips come online, and they will, especially some interesting programs I'm in right now, these quantum chips are going to move at near light speed, and they're going to operate anywhere from 100,000 times faster to 1,000,000 times faster than what you're seeing with NVIDIA today.
That's crazy.
It's crazy at 1 nanometer, like really, really small. So we, this is just, so I'm going to look at the audience here. This is where it gets real sci-fi real. But let me give you the breakdown. So if you look at classical chips, traditional chips use what we talked about earlier, electrons, right? And those travel through wires, and those wires are metal layers, and they hit resistance, because as you're moving lots of electron through metal, the more electrons you move at a faster rate, it generates more heat.
Right.
And they slow down as you pack in more. So
Right.
companies like NVIDIA have built this really cool software that helps you like diaspora, like spread it out to create parallel processing. But essentially, most clock speeds of semiconductors are about 2.5 megahertz. But when you look at guys like NVIDIA, they're able to parallel process and essentially replicate 2.5 gigahertz in capability. But now all of a sudden, when you start getting into some things in quantum, you start talking about near light speed, and you're talking about terahertz. Like, wow. That's 1,000,000 times faster than a 2.5 megahertz, and it's 100,000 times faster than the gigahertz. And that's insane. And so when you think about where quantum's going, we're working with organizations and doing some interesting things that, we're part of a coalition called the Magna Carta Project. So it's kind of like the Manhattan Project for quantum. So really, really quiet stuff going on. What I can tell the average person is you really want to look at how we can extend the life cycle. And I'm merely going to repeat what I said on Charles Payne and leave it at that. Is you can get it. Why not leverage 40 years of solid supply chain and semiconductor experience and move quantum computing a little bit back into semiconductors, move things at the speed of light at nanoscale, meaning we can cram way more compute into smaller space, generate less heat, less energy waste, and insane speeds at terahertz. And there's a really cool way to do it. And it's not talked about much. And I've mentioned it a few times, but now I'm starting to abate or slow back kind of how we're getting there, because I've gotten some really insane phone calls and some really crazy internationally known figures getting involved. So we're kind of slowing it down. But what the average person should understand, I think you're going to see two camps emerge.
Yeah.
The current big tech kind of model, which is, hey, let's centralize your data and let's make things room temperature. I mean, let's not make things room temperature. Let's make things super, super cold at absolute Kelvin. And we're going to create these qubits, and you're going to have to come to us. Or some of us, look, it's high risk, but oh man, if we win, it redefines the world. What if you can say, you know what? We're just gonna upgrade the existing semiconductor industry, bring semiconductor manufacturing back to the United States.
Hey, let's pick this up after the break. We'll be right back. You're listening to DM Radio. Okay, folks, back here on DM Radio, time for the podcast bonus segment here with Sean Michael Brehm, bringing manufacturing back into the United States. I hear you're kind of like shifting left on the processor level, right? Isn't that kind of what you're talking about doing? Is like, because this is, I mean, this is what the folks at Intel have done and others around the world for years. It's like, okay, and of course with the GPUs, that's why NVIDIA is focusing so much on that. And they're making a lot of money at it these days. Because if you get down to the CPU level or the GPU level, you focus on the processor and how that's designed.
Yep.
What kind of information flows are you looking for there? What kind of concurrency do you want? Kind of parallelization do you want? You can bake security into chips. There's all kind of stuff you can do at the chip level if
Yep.
you can do that efficiently and bang these things out and get them at nine, 5 nines or whatever it is. But that's kind of what you're talking about, right? It's like let's shift all the way left into the processors, into the chips themselves to be able to enable this kind of quantum effect. Is that right?
That's correct. So how about we go back to the chip? We do some interesting re-engineering on how we use metal, how we use metal layers, how we create controllers, and start moving to nanoscale at nearly the speed of light for less heat, less energy waste, and these insane speeds. And these are things that I've seen. New transistors that would blow your mind. 1 nanometer, 2.5 terahertz. I mean, this exists today.
Hmm.
And so what you're looking at is taking quantum, which is a mind-blowing new way to represent and process data, i.e. many possibilities at once, and you're able to take this hardware breakthrough that can run new data structures fast, efficient, and at scale for a
Wow.
new foundation for next generation computing, leveraging an incredibly proficient industry. But let's not send it to Taiwan. Let's build it back into good old USA. Let's take the innovation we've got here in the US. And look, the people that win, the country that wins quantum computing,
Wow.
this is a sober moment,
Right.
dominates the global economy for the next 100
Right.
years.
Right. Right.
We
Well,
can't keep taking this and taking it overseas. It's not like manufacturing a
wow.
car in Germany because we like a Mercedes Benz. This is
Right.
something that has to be done in the States. And so we're toning things down, making it a little bit more quiet. I got really good board advisors going, Sean, stop talking. So what I can
That's funny.
tell
I get it. No, this is interesting.
Danger, Will
Because
Robinson, right?
yeah, well, at the end of the day, it's always about business outcomes. What business
Yeah.
outcome do we want to get? And this is the big caution I keep throwing out about large language models and the fact that they're wrong 20 to 60% of the time. I mean, a catastrophic number for business outcomes. You have to get your business correct one way or another. And this sort of quantum power is going to change how we do everything, and because you could do it on demand. Like you don't like we used to have to do so much planning, all this data warehousing stuff, like to get all the data in there to be able, you had to know the schema ahead of time. Then we came up with all the schema on read stuff. I mean, I watched the whole Hadoop thing blow up, and it's a file system, right? It's just a file system. You taught yourself Hadoop.
I
You're
did.
able to
Yeah.
use these technologies, and they can be very powerful. But again, it's like I mean, it just reminds me of how sometimes you have to change everything or change nothing in order to get the new results, and it's like it's going to be hard. That's why I like the quantum bridge concept, because you're
Yeah.
understanding that we need some way, we need a flywheel in between the power of these quantum chips and all of our legacy infrastructure and how we operate that. And it's like, okay, it can be done by APIs. It could be done. You're talking about context protocol these days, which is very interesting. It allows the LLM to call your graph, which is pretty cool stuff. So now it's like, got more of a two-way street going on here to get richer context, to get closer. But the people don't realize that the power of quantum computing, if done correctly, can obviate the need for whole swaths of the enterprise technology stack. Security,
Yeah.
we talked about security, data management, analytics, all these
Yeah.
things just kind of spin right out of the box in real time and tell you what to do. I mean, that's when you're getting somewhere, is when it's like, okay, make 5,000 of this product and sell it in Japan. Make 3,000 of that product, sell it in Detroit or whatever. Like
Yeah.
when you can start analyzing the needs around the world and optimize your production line, that's when things get crazy. And I think that's the possibility. Closing thoughts from you.
It's not possibility anymore. It's probability. Like when you see things, what I've seen, I mean, we started the conversation off about your computer, which it's fast, but it thinks in ones and zeros, like flipping light switches.
Right.
You got to imagine your computer that will be able to think in infinite possibilities. So instead of just ones and zeros of a light
Right.
switch,
Right.
that we're going to quantum. Now imagine that thinking happening at near light speed.
Right.
That's the kind of technology that we're seeing already. And it's operating at room temperature. I mean,
Right.
together, gosh, it's so exciting. They're making computing so powerful that it's going to crack complex problems, secure global data sets, run not artificial intelligence, but run authentic intelligence. When shared, becomes collective intelligence. Go look it up. MIT's words, not mine. It's not sci-fi.
Right.
It's the future, and it's being built right now. And I would just tell the average person that's out there, if you're an American citizen, demand that this is built in the USA.
Yeah. Right. Right. Well, there's a real trend to bring manufacturing back to the country. It's going to be an interesting ride over the next year or so as all that sort of shakes out. But Rome wasn't built in a day. Quantum wasn't built in a day. I think that, however, it is, to your point, it is going to revolutionize how we do things. But you need your on ramp. And you made a comment there, and I'll quote, because this morning I talked to that other gentleman. You're going to like him too, Stephen Klein. He made an excellent point about how LLMs are being used today, and it's a very short-sighted, short-term, oh, like cut our costs to be more profitable type approach. We got 10 people, we'll fire five of them, say go use Gen AI to fill in for the other five. Well, that's you can only go so far cutting people to use technology. He said instead, why not focus on investing 1% more in training your people about, he's got something called curiouser AI is what he calls it, because he said you can go to infinity in upside, right?
100%.
And I was like, that's a quote. That's
Yeah.
interesting. You can only
Infinity.
cut costs so much before you got nothing left. I've seen this happen at companies. It's like they're not just cutting fat; they're cutting, myofascial and bone and everything. It's like, all right, well, that's going to cause you some problems. But upside can go to infinity because you can come up with new products, new services, new ways of doing things, new clients, all that stuff. And that's me. I'm an upside guy. Like I'm a supply side, I guess. I think, hey, man, let's make cool stuff. I can always make money to pay for it, right? But it's
Yeah.
like, you do need to have some sense. But anyway, folks, look this gentleman up online. It's always a pleasure talking to him. Sean Michael Brehm, Brehm, Spectral Capital. They are OTC, FCCN, I believe are the call letters, FCCN. So look those guys up. Fascinating stuff. I'm sure you'll be hearing more from him in the future. We'll talk to you next time. You've been listening to DM Radio.